This section on the mean value theorem is one of those sections that seem to deal more in theory than in a lot of examples. But nonetheless, it's very important stuff because the mean value theorem kind of works in the background to solve a lot of calculus, to make a lot of calculus happen. Well, I'll start with the result and we'll go from there. Like I said, it'll be a lot of theory and proof kind of stuff. I'm going to start with something called Rolle's theorem. Now suppose f of x is continuous on the closed interval AB and differentiable on the open interval AB. You'll see this a lot, being continuous on the closed but differentiable on the open. That's because we have continuous, we talk about being left and right continuous at endpoints, but a lot of times with derivatives we need to have space around the numbers that we're dealing with. Anyways, if f of A equals f of B, then there is a number C in the open interval AB, that means C is between A and B, with f prime of C equal to 0. So in particular, a quick picture might look something like this. You would expect this if you were to have any kind of a function from A to B that's continuous on the whole thing and differentiable, you know, there as well. If I'm going to, unless I have to have them start exactly at the same height, sorry. Now if you have them starting at the same height, you could go there directly across, and then the derivative is 0 for every number in between. But basically, if you leave A, you've essentially got to come back down if you ever hope to get to B. And then right here could be where a C occurs. And it could happen in more than one spot. Like you could have it, another C could happen over here, for example. So, here's how it works. What we call a proof of it is, we know since f of x is continuous on the closed interval AB, it attains an absolute max and an absolute min somewhere in AB. Alright, so what if it attains a max? Okay, so if, let's say, we have the possibilities are going to be endpoints or points in between. So potential places for an absolute extrema are at endpoints and critical numbers. So let's start with the endpoints. Let's say f of A is an absolute max. then we have to have an absolute min somewhere in the interval, because if f of b could not be an absolute min, because if it was, the absolute max, where is it at? We were assuming that f of a equals f of b. So if f of b is an absolute min, then the absolute max equals the absolute min, and the only way that can happen is when the function is zero. No, sorry, when the function is constant. Sorry. If the function is constant, its derivative is zero. So that's not a big deal. If f of a is an absolute max, then f of b is also an absolute max. So the absolute min has to be somewhere in AB. Say at x equal to c, which is in AB. And then we know at that particular place, so we know that f of c is an absolute min and a local min. So f prime of c equals 0. And then if you don't assume any of these happen, you don't have a max, an absolute max, or min at the endpoints, it's even easier. You'll have more points in the interior that can give you places of 0. So that's not that big of a deal. Alright, here's A and B. Let's start with the first one. Sine is differentiable everywhere, so it's going to be differentiable on any interval you give it. So it's going to be differentiable, it's going to be continuous, it's going to be everything. So this function will work. And the second one, we know that the absolute value has a sharp point at x equal to 0, which is inside of here, so this function is not differentiable. On the open interval -1 to 1. In fact, it's 0 that is the problem. I'll say not differentiable at 0. So let's work part A and see if this satisfies the other two things. So we've got differentiable and we've got continuous and all that. Let's try sine of 2 times 0, well, that equals 0. And then sine of 2 times pi over 2 equals sine of pi, which equals 0. All right, so we got that going for us as well. So then there's got to be some place in between 0 to pi over 2 in which the derivative of this function equals 0. So let's take the derivative. F prime of x equals cosine of 2x times 2. Don't forget to take the derivative of 2x. Now then, I need to solve this equation. 2 cosine of 2c equals 0. Because c is the number I'm looking for. I'm going to divide by 2. So cosine 2c equals 0. Where's the first place where cosine is 0? Cosine is 0 at pi over 2. So that says that 2c equals pi over 2. And then I can divide by 2 to get c equals pi over 4. So there we go. That is, in fact, in the open interval from 0 to pi over 2. Good. Now, this part here, though, let me see if we can actually find a c for it to work, even though it's not guaranteed, just for the fun of it. B, f of x equals 1 minus the absolute value of x. I have taken the derivative of the absolute value of x before. F prime of x, we'll see if you remember it. It's negative the absolute value of x over x. Or you can have it upside down, it doesn't matter, it's the same thing either way. Now, is there a place where this is going to equal 0? Alright, if I'm going to equal 0, I would have to multiply through by x, and I would have negative absolute value of x equals 0, or just the absolute value of x equals 0. And then x would have to be 0. The only number whose absolute value is 0 is 0, so x equals 0. But this is not differentiable at 0. So there's no answer for what happens at 0. Let's move on to the big theorem, and that's the mean value theorem. Suppose f of x is continuous on the closed interval AB and differentiable on the open interval AB. Then there is a number C which is in the open interval AB where f prime of C equals f of B minus f of A all over B minus A. Now, what exactly is this supposed to be saying? This here, all this stuff, let me draw a picture of this and it'll be a lot easier to understand, I hope. And then we'll work on a proof of it. Once again, we're defined on A to B. The only reason I make my functions the way they are is so that I can draw the pictures easier. So let's say at A, we have something in a B. It doesn't matter if it's higher or lower, I just want them to be different. They could be the same, it really doesn't matter, but let's say we come in and do something like this. Alright, there are two ways to envision this thing. Let me put the points here. This is B comma f of B. That's the right end point. Over here is A comma f of A. Now into this, I want to see if I can draw a secant line. Not too bad. We're going to call the secant s of x. I'll get its equation in a minute. And then look around here and take a look, and if you can see a space somewhere where the tangent line looks like it would be parallel to the secant, because this in fact is the slope of this secant that I just told you about. So I want to look in places where the derivative might give me the same number. That would be places that would have a parallel tangent line. So maybe it might be around here. Let's see how it looks if I extend it out in the way of tangent. So that's possible. That's possible. That could be a tangent is parallel to secant. And where is this particular number? Well, that's supposed to occur at this magical number of C. Right there. So that's the idea. There's going to be some place where the secant line equals the derivative of some interior point. Let s of x equal the secant line. So in particular, s of x is going to equal, let's take a look, what's the slope of this line? That's this stuff right here. So it's going to be f of b minus f of a all over b minus a times x minus a plus f of a. And this should look very familiar to the linearization, which this has a lot to do with that secant line. The reason why this is, think of this as your f prime of something, or just m. You have an m, change in x plus y. On the other hand, the tangent line has a slope f prime of c. And I'm hoping that up here I'll have the same m. Assuming that b does not equal a, and we wouldn't talk about this if b were equal to a, there's nothing to talk about in that case. So assuming that b is not equal to a, b is bigger than a, then this thing right here is not going to be undefined. So I'll have a number times x minus a plus f of a. This is completely differentiable and continuous anywhere you can possibly need it to be. It's basically, it's just a line. I am going to set g of x is going to equal s of x minus f of x. Okay, now let me plug in the endpoints for g. G of a equals s of a minus f of a. So let's plug in a into the formula for s. If I replace x with a, I will get a minus a here, and this whole part will be 0, and I'll be left with f of a. So I'll get f of a minus f of a, which will equal 0. And then g of b will equal s of b minus f of b. That equals, if I replace x with b, this part here will become b minus a. So I'll have f of b minus f of a all over b minus a times b minus a plus f of a minus f of b. Let's see, cancel, cancel. And you see you got f of b minus f of a plus f of a. The f of a's cancel, but you also have f of b minus f of b, so the f of b's cancel, and that equals 0. So here I've got a function. G is made up of two functions that satisfy everything we needed to satisfy. That they're differentiable on the open interval, continuous on the closed interval, because I'm just taking the difference of them. So whatever each of these functions has, the difference does as well. So what do we have? I have g is continuous on the closed interval AB and differentiable on the open interval AB. So there is a C in that open interval AB where g prime of C equals 0 by Rolle's theorem. Well, if g of C equals 0, what do we have then? G of x equals s of x minus f of x. So g prime of x equals s prime of x minus f prime of x. So g prime of C equals s prime of C minus f prime of C. But I was told that equals a 0. So I get s prime of C equals f prime of C. However, remember s of x equals f of b minus f of a all over b minus a, slope of the secant line, times x minus a plus f of a. Take the derivative, and I'll get s prime of x equals, well, there's only one x in here, so the derivative is this. Well, that's the same as f prime. S prime of x constantly equals this. Well, that means that s prime of c will also equal that. Well, and that equals f prime of c. And there you go. All right, I wanted to do a couple of examples, some numerical examples with the mean value theorem. And so I'm going to start with this question. There's three parts to it. First is determine whether the mean value theorem applies to the following functions on a closed interval. So let me do part A first for these things. Inverse sine, all the trig functions are differentiable wherever they're defined. So inverse sine is defined for x between -1 and 1, and 0 to 1/2 is certainly within that realm. So that's not a problem here. G of x is going to work for part A. J of x, this is a nice continuous function. However, when you take the derivative, J prime of x will equal 1/3 x to the -2/3. And the negative exponent means that I will not be able to put in 0. So it's not differentiable at x equal to 0. So the second one, might as well cross that out. And let's see, then we'll continue on with what part B says for us to do. Now let's find the points that are guaranteed to exist by the mean value theorem. And what are those? We are supposed to have G prime of C is supposed to equal G of B minus G of A all over B minus A. C is some number that's between B and A. All right, my B then is 1/2, and the A is 0. Oh, while I'm over here, the derivative of inverse sine is 1 over the square root of 1 minus x squared. So this left side becomes 1 over the square root of 1 minus c squared. And then let me put these numbers in here. We have sine, inverse sine of 1/2 minus inverse sine of 0 all over 1/2 minus 0. Let's see, inverse sine of 1/2 will give us pi over 6. Inverse sine of 0 is 0. Of course, you can rewrite this as pi over 6 times 2 over 1. So that equals pi over 3. Okay, now that's part of the problem. I still have to figure out the c, and I've got to make sure that the c falls in the interval from 0 to 1/2. So what I'll do is let me rewrite this. Well, let me put it down here. 1 over the square root of 1 minus c squared. First thing I'll do is cross multiply, and I'll have 3 equals pi times the square root of 1 minus c squared. Let me square both sides, so I get 9 equals pi squared times 1 minus c squared. I'm going to divide by pi squared. then I'm going to swap places with c squared and 9 over pi squared. And then let me go ahead and take the square root. Don't forget plus or minus 1 minus 9 over pi squared. Now, this is supposed to be in, c is supposed to be between 0 and 1/2. So that takes away the minus sign. So c equals the square root of 1 minus 9 over pi squared. Just to be on the safe side, I'm going to check to see if this is in between 0 and 1/2. So I will go to the calculator to make that calculation. Second, square root 1 minus 9 divided by pi squared. Enter. 0.297. This is approximately 0.297. So this part right here checks. So there's the value of c that is guaranteed by the mean value theorem. Another example I wanted to do was slightly more theoretical than the previous ones that I did. Let's take a look at part A of these questions. It says, show that the point C guaranteed to exist by the mean value theorem for f of x equals x squared on the closed interval AB is a plus b over 2, or what they call the arithmetic mean. So let me go ahead and start part A. Alright, so according to the mean value theorem, we're going to have f prime of c is going to equal f of b minus f of a all over b minus a. Well, the function was x squared, so f prime of c is 2c, f of b is b squared, f of a is a squared over b minus a. And hopefully you can see where this is going to go real quick. I can factor b squared minus a squared because it's a difference of squares, and you'll get b minus a times b plus a divided by b minus a. And we can cancel the b minus a's. So I have 2c equals b plus a, and then divide by 2 to get the result. Part B, we are dealing with the function 1 over x. Here, the c that is guaranteed is what they call the geometric mean of the numbers a and b. So let's go ahead and do that one. So once again, I'm supposed to have f prime of c equals f of b minus f of a all over b minus a. Now, f of x was 1 over x, so f prime of x is negative 1 over x squared. So I'm going to get negative 1 over c squared, and that's supposed to equal f of b is 1 over b, f of a is 1 over a, divided by b minus a. And of course I'm going to simplify the right hand side until I get anything close to what they have on the other side. So I'm going to get a common denominator in the numerator for the right hand side. So when you do that cross multiplying business, and I'll get a minus b all over a times b, and all of that is divided by b minus a. Now you might want to think of the b minus a as being b minus a over 1 so that you know how to do the next step. I'm going to flip this bottom fraction, and I'll get a minus b over ab times 1 over b minus a. And I can cancel the a minus b and the b minus a, but I'll leave a negative 1 in its wake. Well, that's not so bad because I got a negative on both sides. So if I multiply both sides by -1, I'll end up with 1 over c squared equals 1 over ab. That means that c squared equals ab, and that c equals plus or minus the square root of ab. Now let's take a look back at the question, because I don't remember ruling out the negative outright. Let me see what the rules were, and we'll see how to answer this. Okay, a and b are positive numbers. Okay, then that means that c has to be between a and b, which means c has to be positive. So we have 0 is less than a, which is less than c, which is less than b. So this means we must choose c equals the positive square of ab. Now before I do the rest of this, let me write this down. Whenever I mention an interval I, but don't specifically say what kind of an interval it is, I mean that I is going to be like something like AB, or I equals AB, or I equals AB closed, or I equals AB. Maybe even I is an infinite interval. The reason why I don't want to mention is because there's way too many cases to talk about. So instead, when I mention I, just keep in mind that any of these are possible. If I just say it's valid on interval I, then it's good for all of these kind of intervals. So with that in mind, let me bring up a theorem. If f of x is differentiable on an interval I, and f prime of x equals 0 on I, then f of x is a constant function on I. Let me just tell you what I'm talking about here. If you have an interval, let's say a to b, and I know that for the entirety of that interval, my derivative is 0. That means that the tangent line is always horizontal on the whole thing. Then this function has to be constant on at least that interval. Now, it can do whatever it wants outside of the interval, but on the interval, it has to be constant. To see why this is true, let x1 and x2 be any two numbers in I, but x1 does not equal x2. Consider the closed interval x1 to x2. By the mean value theorem, there is a number c with x1 less than c less than x2, and f prime of c equals f of x2 minus f of x1 all over x2 minus x1. However, since c is in the interval, it's between these numbers, so it's definitely in the interval, f prime of c is equal to 0. Now, I'm assuming that x2 and x1 are different, so I'm going to multiply through by that. And then add f of x1 to both sides to get f of x1 equals f of x2. What I did is I picked 2 points, any numbers that were not equal to each other, and I just showed that their y values were the same. This implies that f is constant. Constant means exactly that. F of any number is the same as f of any other number. Let me close out the theory with one last theorem. If f prime of x equals g prime of x for every x in an interval I, then f of x minus g of x is a constant. Well, there's not much to do here except when I say that f prime equals g prime for every x in there, that obviously means they're differentiable on the entire interval. So you could define a function, say h of x to equal f of x minus g of x, if you want. Then, since it's the difference of two differentiable functions, h of x is differentiable, so it follows all of the things about the mean value theorem that we had before. And so, in fact, I can use the last theorem that says here we have h prime of x equals f prime of x minus g prime of x. But but I know this is equal to 0 because f prime equals g prime. So that means that h of x, which equals f of x minus g of x, is a constant. In particular, this is not part of the proof, but I think you might find it. In particular, f of x equals g of x plus c on I for some constant